we know that it works. This is the fundamentals of knowing why your circuit is working, because I would hate for you to get to DCS, plug it straight into BIOS, and then you're like, damn it, it's not working, why? So we know it works. Let's get into the fun stuff and get it coded to DCS BIOS. What's happening, guys? Scott from a Hornet's Nest. Welcome back to episode 10 of Tutorial Tuesday. It's so good to see you. And in today's episode, we are going to be upgrading the wiring on the F18 sensor panel to reduce the amount of inputs going to Arduino, saving you time and money. Now, you're probably asking yourself, what do I have to replace about this? Because it looks pretty good, and it does. It's a full functional sensor panel, but I'm going to make it a little bit more efficient. I'm going to show you how to do that with some real basic electrical items. If we have a look at the sensor panel from a top-down view, it actually looks pretty good. It's got the radar and INS multi-position switches, and we've got our toggle switches at the top. But if we turn the panel over, you can see that these multi-position switches are absolute pin hogs when it comes to how many pins are required going to the Arduino. Now, I have this running with a multiplexer, which is a bit of a complex way of doing it, but I'm going to show you how to reduce 12 pins, which is 8 on the right, 4 on the left, down to 2 wires, and it's real simple, as we're going to be using theory that we learned in episode 9 when we learned about potentiometers. But before we can do that, let's have a look at the anatomy of one of these switches away from the complexity of the panel. These are the stock standard switches we'll be using. These are the C&K A125s. They're a 8-position, 45-degree throw multi-switch. And the anatomy of them, we have the pins on the outside which connect to each position, and we have a common pin in the middle which has a wiper blade assembly connecting those pins as the knob rotates. Now you might be thinking, we just learnt about something that had a wiper pin, and that's right, we learnt about the potentiometer. It was a wiper pin connecting onto a resistive strip. So the only difference between this and a potentiometer now is this has detents or fixed positions, whereas the potentiometer is smoothly operated, and we don't have a resistive strip. But I'm about to show you how to create your own resistive strip, turning this into a detented potentiometer, allowing you to pull position values based off its analog value. So how are we going to do that? Well, you're going to need 7 resistors of equal value, and anywhere between 1000 and 2000 ohm resistance is great. And you need a couple of wires to connect it to your Arduino with a suitable connector type of your choosing. Now, if we take one resistor and solder pin 1 to 2, 2 to 3, 3 to 4, all the way through to pin 8, but don't connect pin 8 and pin 1, you'll now see that we've got to create ourselves a resistive band. Now, this orientation of how the switch is with pin 1 in the bottom left now starts looking exactly like a potentiometer. Now, if you remember last episode, when we want our value of our position or the ADC value to increase, we want to turn towards 5 volts. So we're going to go and connect the ground to pin 1, 5 volts to pin 8, and we're going to connect the signal cable going to Arduino through the common pin here on the middle. Now, what does that look like on the actual switch? Well, we went and actually did this episode 1 and 2 when we created the F5 button box. And this is the switch from that exact model. You can see here, we've got our resistive strip forming around the outside with each resistor connected to a pin, leaving pin 8 and 1 unconnected. And then we've got a yellow wire, which is our signal wire going to the common pin. And then this is the orientation that it would be in your diagram. We have pin 8 connected to 5 volts and pin 1 connected to ground. And it's as simple as that. But if you go and create this, it's ready to go. You don't need to add anything extra. But do you think we could make this look a little bit neater? Yes, we can. It's a Hornet's Nest. We make everything look neat. We go a little bit above and beyond to make it look cool as well. Now, this is where today's sponsor's coming in, because PCBWay has generously provided the circuit boards for today's lesson. And instead of putting the resistors to the switch itself, we're going to dive into surface mounted components, and we're going to create a little breakout board. And it is no bigger than the switch itself, keeping that profile nice and sleek. Now, a bit about PCBWay, for those that don't know, they're your one-stop shop. They are going to be everything you need to create your cockpit, and you don't even need to know how to do any of the manufacturing, because they do 3D printing, laser cutting, they've got a 5-axis milling machine, and they've got PCB production and PCB assembly. So you don't even need to know how to solder, and you're going to be on your way to creating your cockpit. And to say thanks from PCBWay and myself, there's a link in the description below to give you a bit of discount on your first order. So Let's get into Fusion, and I'm going to show you the schematic behind the circuit board, and then we're going to show you what the board looks like. So here we are in Fusion with the schematic loaded up, and as always, I put my processors in the middle, inputs on the left, outputs on the right. In the middle, we have the symbol for our switch. You can see it's got pin 1 to 8. On the left, we have our inputs, which are all our resistive bands. And on the right, we have our outputs to Arduino. Now, you're probably looking at this and saying, Scott, you never told me I needed a capacitor or a resistor. You don't. You definitely do not need this little bit of the circuit, but it's a nice to have because the capacitor will give you debouncing and noise filtering, and then the little resistor will stop you potentially overcurrenting the pin into Arduino. But again, if you wanted to go down this route with the resistors around the outside, you definitely do not need this. It is a nice to have. We can see that we've got pin 1 connecting to ground, pin 8 connects to 5 volts, and the rest all connect to their respective pin names here. We're running a 2.2 microfarad capacitor in a parallel, and then we've just got a 100 ohm current limiting resistor going to the input of Arduino. And this here is our trusty JST PH connector. You can go have a look at our 2D board now, and we can see that the top layer is red, and that's where I've put a ground plane, because I want the bottom layer to actually have the traces and components on this time. That way, when it's all soldered together and we connect it to the switch, if I've got to replace any broken resistors or capacitors, they're easy to access. We then push that to a 3D view, and we can have a look here. This is what it's going to look like. And that's pretty cool. It does look incredible, and you can see we're not using the little blue through-hole mounted resistors. We are now going to become a little bit more professional, and we're going to use surface mounted resistors. Why? Because they're smaller, more compact, a little bit cheaper as well, and they're so much easier to solder if you have the correct equipment. But remembering, you do not need to go down and buy a ton of equipment just to get this done. I've shown you here that with a soldering iron and 7 resistors, you can do it yourself. The components we're using here are the JST PH, which has the 2.0mm pitch. They're just my favorite ones to use. And we're using 1206 SMCs or SMDs, depending on what you want to call it, surface mounted component or surface mounted device. It's the same thing. 1206 is just its dimension. It's 0.12 of an inch by 0.06 of an inch. Then you can see here that our switch then goes through the through holes, and they will just solder on normally with an iron and solder. Now that we know how the design came about, let's go and solder this. And if you want to follow along at home, I'm going to provide you a couple different ways how to do it. On Cults 3D, I'm going to put all the Gerber files so you can go and send it to a manufacturing house yourself, or I'll give you a link for PCBWay that will have it there ready to go and you can just purchase it straight from their website. So let's head across to the soldering station and get soldering so we can connect this to DCS BIOS and get it working in the F18. Alrighty, so here we are at the solder station with the circuit board ready to go. We're going to tip out 7 1000 ohm resistors, and we're going to tip out a capacitor as well. The code for the size of resistor is on the back of the device itself, and for your capacitors, it is printed on the reel. I'm going to use quick flow solder here to make easy work of it, and you can see it's hard to actually push out of the tube. So the easy way to fix that is to apply some hot air to your board and apply hot air to the needle as well. Now you just want to go and put a dot of solder on each of the pads, and you'll learn over time how to judge how much you need. But if there is too much, just remove it so it doesn't make your board messy. Now all we've got to do is apply the components to the board, and then we can place it on a metal helping hand so we can apply hot air to the board, reflowing that solder. The nice thing about reflow solder is it will also center the component just with the surface tension of the liquid solder. But don't think you need to go out and buy an expensive hot air station. You can also do this with a soldering iron. Just make sure the temperature of the soldering iron is turned down to about 230 degrees. Now just add a little bit more solder to those that didn't get quite enough. And now we can go and add our JST connector, and you can see that I'm taping it down so we can turn the board over and the JST won't fall out, so we can apply solder to the 3 pins. Have a good inspection of your board before you go and apply the switch. Now all we've got to do is fit the switch, add it to another set of helping hands, and just solder it to its pins. Have a test fit of the JST connector. Now all we have to do is assemble the panel. and tightly fasten the switch to the back plate. Test fit the text panel to make sure it fits nicely. Then we can go and fit the JST connectors to the back of the switches, that way it's easy to access before we add the circuit board. Using M3x10 bolts, we attach it to the circuit board standoffs. Then we just go to apply the knobs, and there we are, all done. So we're back from the solder station, and all we got to do now is code it to Arduino, and I'm going to show you two ways of coding it. One, how to get the actual analog value, or what's correctly called the analog to digitally converted value, the ADC, and then how to connect it to DCS BIOS, so you don't even have to worry about the complexity of it. So if we have a look here, we've got our panel ready to go. We have the radar switch connected to a green signal wire, and we have the INS switch connected to a yellow signal wire, just so it's easy for us to see on camera. All we've got to do is connect the respective grounds and 5 volts to their correct pins. So we'll go and plug 5 volt in there, ground in here, and we're going to connect radar to A1. We're then going to reconnect the ground and 5 volts on the INS switch, and we're also going to connect its signal pin to A2, just so it's easy to remember. And there's a ground here and a 5 volt here. And you can see by using circuit boards on the back of your panel, we don't have to waste all the 5 volt pins because it will connect to its own system. But for the purpose of prototyping today, that's why we're using so many 5 volts and grounds. Now, would it surprise you if we go into Arduino and we realize that it's the exact same code as episode 9? Why? Because we have essentially created a detented potentiometer. So the code shouldn't change. So we can go here and I'll even show you, this is the same code with pot pin, pot value, pot pin as an input, and we're going to print the pot value, right? And it's connected to A1. Well, radar is connected to A1 and it's in position 1 or position 0, which is, we're expecting a 0 out of 0 to 1023. Now let me just show you. If I go upload, uploading, I hit the serial monitor, it's showing me a ton of zeros. Now if we go to position 2, we're now getting 144, which is pretty good. Position 3, we're getting 290, 291. Now the question is, why is that working so well? Because we knew the theory, we've applied it, and now it's working. But let's use a bit of camera magic. Let's get rid of pot pin and pot value because it's providing us nothing but confusion. Let's call it something appropriate. And just like that, we've got the INS pin connected to A2 now because it is connected to A2, and I'm using the INS pin because I want to show you all 8 values. But how do we know that we've done it right? Because we could easily take this, skip this step altogether and go to DCS BIOS. But then what happens when DCS BIOS isn't responding the way we're expecting it to respond? Well, if you don't know the theory behind it, you're not going to know how to fix it. And that's what I really want to get through today, is know the theory so you can fix it. It's all fun and games for me to tell you how to do it, but then I'm not going to be there when it's not working. So if you know how to fix it, you don't need me anymore. So for us to know that it's working correctly and if we've soldered it correctly, by identifying what the value should be, so it's not a surprise to us when it shows up. And to do that, we're going to look back at the screen here and do a quick voltage dividing lesson. And that is to calculate the voltage coming through the signal wire based off the resistance on either side of the wiper blade. So if we want to go and identify what the voltage coming through the signal wire is, if we turned it to position 4, the formula is voltage out equals voltage supplied times R2 divided by R1 plus R2. Now when I say R1 and R2 now, I'm not referring to this little resistor and that little resistor. It is talking about the voltage on either side of the wiper blade. R1 is the total resistance on the side between 5 volts and the wiper, and then from the wiper to ground is R2. So if we go and plug all that in, voltage supplied equals 5, R2 is 1, 2, 3, and we use 1000 ohm resistor, so it's real easy to calculate. So we've got 3000 ohms divided by R1, which is 1, 2, 3, 4, which is 4000 ohms, plus R2, which is 3000. You go plug that into a calculator and it's going to spit out 2.143, which means it is 2.143 volts going to Arduino to be calculated and then converted to a value between 0 and 1023. Now, for us to calculate what Arduino is going to calculate, we're going to do it in the calculator as well. And that value is ADC equals 1023, which is our range that it can be, divided by 5 volts times V out. And if we put that into the calculator, position 4 should read 438. Now, you might get a couple of digits off because of the circuit that you've designed and just the power that you've actually got going through, but we're going to get pretty close. So let's have a look what position 4 should look like when we go and run this bit of code. There we go. Serial monitor. Well, position 1 is reading 0. Let's go 1, 2, 3, 4. And we're getting 437, which is pretty close with a bit of rounding errors and a circuit that is not a perfect. You're going to lose a bit of volts on the way, but that's pretty cool. Now, if we go and tabulate this quickly, we can go and have a look. If we go tabulate the rest, so we don't have to do the calculations together, we can see we're reading pin 1, which is 0, position 2, 144, 290, 437, 438, 582, 731, 732-ish, 878, 1023, and then it will go back to 0 when we click it once more. So we know that it works. This is the fundamentals of knowing why your circuit is working, because I would hate for you to get to DCS, plug it straight into BIOS, and then you're like, damn it, it's not working, why? So we know it works. Let's get into the fun stuff and get it coded to DCS BIOS. So to code it to DCS BIOS, we're going to need to go open examples, DCS BIOS, and we want to open up a new IRQ serial. Delete that top text because I don't like messy looking code. Add our spaces, but what do? We add variables at the top. Let's go and define these variables. We've got radar int radar switch equals A1, int INS switch equals A2. Look at that, that's pretty cool. DCS BIOS.h, it's including that. Paste your code snippets. How do we get the code snippets? We go to our desktop where we saved it. If you haven't watched episode 7, go have a look. This is how to get everything DCS BIOS. We're going to open up Bort, and we're going to be prepared for it to open, close, and reopen again. We're going to go to the top left. We're going to select our module. We're going to go to the category, and we're just going to find the sensor panel. Scrolling all the way down, we can see we've got the INS switch, and a little bit further down, we've got the radar switch. Now, we're going to have a look at a whole new string that we haven't looked at before in our DCS BIOS lessons. Let's go and deal with the radar switch first so we can keep it in order, and we're going to go to the radar switch off, standby, operational, and emergency. Well, we're not going to be using a rotor encoder because it's a multi-position switch. We're not using constant bytes because we don't want to go and hard code each of these 4 pins because that would just waste a ton of pin space. Now, if that was the only switch in your cockpit, sure, it's a bit easier. But we want to go down to this one, which all of you have probably dismissed, analog multi-position. What have we done? We've created our multi-position into an analog value, so this is the one we want. Let's go click the copy icon, and we're going to go back to Arduino, and we're just going to move Bort out to the right on a separate monitor. Control V to paste it. So we've got the DCS BIOS library with an analog multi-position function. Radar switch in orange is the name DCS BIOS has given it, and radar underscore switch is the in-game name. Then pin, steps, and resolution per step is what we can input ourselves. Well, the pin's pretty easy. For the radar, it is the green pin connected to A1, so we can type in A1. No, we don't want to type in A1. We want to use our variables. We don't want to hard code into our main body. So let's go and use our beautifully made variable radar switch. The steps is how many positions or how many pins on your switch have you connected to the band? Well, we've connected all 8. It's an 8-position switch, so it is 8 steps. Resolution per steps, well, we knew when we connected to pin 1, it was an input of 146, and it will just, because it's a linear band of resistance, it will just keep going up in multiples of 146. So the resolution is 146. Great. Well, instead of uploading, we can just go compile. And that way we don't have to try hang the Arduino trying to upload if it's wrong. Let's just have a test. Verify or compile, depending on your Arduino version you're using. I'm going to hit verify. And we come up with an error straight away. And if this is your first time coming across an error like this, because you've been pretty successful with your BIOS coding, don't stress. I'm going to show you exactly why it's caused and how to fix it. And it all comes down to this line here. It's talking about the analog multi-position function within the DCS BIOS library. It refers to analog multi-position with a constant character with a message, and that message is radar switch, a character type symbol for pin, and we've got that there, and then it comes with character number of steps, which we have is 8. But you can see in this little bracket, there is no reference to resolution because it doesn't exist anymore. They've removed it completely. And if you look at the backend coding, you can actually see they calculate it for you, which is super nice. So let's go and delete the resolution and its associated comma. So all we have now are 3 variables within that brackets, the game's name, our variable that we created, attaching it to pin A1, and 8 steps. Let's go verify. Beautiful, no errors, it's done compiling. Now we know that is how to correctly do it. So let's bring Bort back and we are going to scroll all the way up to INS. INS, and it's 8 positions. And we're going to go straight to DCS analog multi-position INS switch. Copy. Enter it on the bottom. We're pretty much done with Bort now, so we can close it. The pin we're using, remember we've got a variable for it. INS switch is in the backend. Arduino will convert that to A2. We don't have to hard code. How many steps? 8. Resolution, well, we know we don't need that now, so let's go and delete it. Now you can see that the pins for the radar switch is the exact same as the INS. It's not talking about the physical positions. It's talking about how many pins are in your circuit that you've connected up. And we've connected all 8 up. There we go. Now the void setup will run once and it's going to run our DCS BIOS setup. Our void loop will run all the time and it's going to loop the DCS BIOS scripting. So we are pretty much ready to go. Let's go upload and get this working with DCS. Done compiling, done uploading, we can get out of it. We want to open up our connect serial shortcut. That's either going to be in your programs folder in your saved games, or it's going to be on your desktop if you followed along with episode 7. We want to double click. Let's preempt COM port number 3 because that's what we're using. If you don't know what your COM port is, go back to your sketch, click where your Arduino label is, and you can see I am connected to COM 3. You enter whatever is connected to yours. Let's go now and open up DCS, the game, and we're going to load ourselves into an instant action mission. Alrighty, so here we are, cold and dark in the jet, everything is off, and our switches are aligned. Now, if your switches aren't aligned, that's okay. It will poll it for you and just center whatever your cockpit state is. Let's go Alt-Tab, open up our connect serial port, and we're going to press enter on 3. We see all of our status. It will give you an error if it's not actually connected. And now you can see all the lines of code running. Keep it open though, so just click back into your game and we are ready to go. So we'll turn our radar to standby and it's pretty instantaneous and it's really cool. And then we're going to turn to operational. And then let's try turn to pull emergency. It doesn't turn. Why? Because the game is actually expecting us to pull up, then turn. So that's not actually connected. And now we're going to go back to operational, back to standby. and we can test all 8 positions of the INS. And you can turn that switch as fast as you want. You don't have to worry about the debouncing because they've done it all for you in DCS BIOS. We can go straight to ground and it will get it there without fail. So there we have it. We have pretty much gone and saved 10 pins on an Arduino. So we could go run this on a Nano with no complex multiplexing, just the use of a bit of potentiometer theory using voltage dividers. So I hope you got something out of it. And in the next couple episodes, we will be starting the F18 build, which I'm so excited about. So go enjoy your week, go try this out, see what else you can save using this theory, and I'll see you in the next episode.